In this question, an experimenter carries out a redox reaction, and this is the equation that describes what happens. Now be careful because it tells us it's unbalanced. So this equation has not been balanced. Our goal is to find an equation for this reaction that is balanced in terms of both the number of atoms, the number of electrons that have been transferred, and the charge. So our first step to doing that is to figure out what is happening in this redox reaction. What's being oxidized, what's being reduced. So to do that, we're going to follow exactly the same process as in the previous skill, looking at the initial and final oxidation numbers of each of our elements, looking at the gain or loss of electrons for each element, and figuring out what's oxidized and what's reduced. So I'm going to go through this fairly quickly since we've already practiced this in the previous skill. So I'm going to write this out a bit bigger. So firstly, in this compound, we have nitrogen and oxygen. Oxygen has an oxidation number of -2 unless it's combined with fluorine. So we're going to have -2 for oxygen initially. Then I can find the oxidation number of the nitrogen by calculating out for this entire polyatomic ion. So we have nitrogen plus 3 oxygens equals -1, since the charge on a polyatomic ion is equal to the overall oxidation number. And the oxidation number of oxygen is -2. So we have nitrogen plus 3 sets of -2 is equal to -1. So that's nitrogen minus 6 equals -1. So adding 6 to both sides, that gets me 5 for my oxidation number of nitrogen. Next, we have I2, diatomic iodine. We know that the overall oxidation number of this is 0 since it's not charged. And since the only thing in it is the iodine, that means iodine must also have an oxidation number of 0. In the products, we have iO3 minus. Oxygen has an oxidation number of -2. So we can go ahead and calculate the oxidation number of the iodine by looking at our overall polyatomic ion. So we have 1 iodine plus 3 oxygens, and overall that has a oxidation number of -1 since that's the charge on a polyatomic ion. So iodine plus 3 oxygens. Oxygens have a oxidation number of -2. So we have iodine, and 3 times -2 is -6. So iodine minus 6 is equal to -1. So the iodine ends up with an oxidation number of 5. Finally, in this compound here, the oxygen is going to have an oxidation number of -2. So we have 1 nitrogen plus 2 oxygens, and we have an overall charge of 0 on this compound, and therefore an overall oxidation number of 0. So that's nitrogen plus 2 sets of -2, since oxygen has an oxidation number of -2, equals 0. So nitrogen minus 4 equals 0. That means the oxidation number of nitrogen must be 4 in this compound. So next, let's figure out if each of our elements have gained or lost electrons. Nitrogen went from an oxidation number of +5 to +4. So nitrogen is becoming less positive in terms of its oxidation number. So getting less positive, that's the same as getting more negative, which means gaining electrons. So we have a gain of electrons for nitrogen. Oxygen had an initial oxidation number of -2 and a final of -2 as well. So we've had no change here, no gain or loss. The answer is neither. And iodine had an initial oxidation number of 0 and a final oxidation number of 5. So iodine is getting more positive in terms of the oxidation number. Getting more positive is the same as getting less negative, which means a loss of electrons. Finally, we need to figure out if oxidation or reduction has happened for each of these. Nitrogen gained electrons, and gain of electrons means reduction. So nitrogen has experienced reduction. Oxygen experienced neither gain or loss of electrons, so oxygen has experienced neither oxidation or reduction. Iodine has experienced a loss of electrons, and loss of electrons means oxidation. So iodine has been oxidized. So now that we know what's been oxidized and what's been reduced, our next step is to write out two half reactions, one for the reduction part of the reaction and one for the oxidation part of the reaction. So for the reduction part of the reaction, that involves nitrogen. So looking at our equation, we have NO3 minus goes to NO2. So that's going to be our reduction part of the reaction. Then for the oxidation part of the reaction, that was iodine that was oxidized. And in our equation, we have I2 goes to IO3 minus. So we've got I2 goes to IO3 minus. So those are our two half reactions. Now we need to balance these. So our first step to doing that is making sure that our elements other than oxygen or hydrogen are balanced. So in the reduction reaction, nitrogen is our element that isn't oxygen or hydrogen. We've got one on the left and one on the right. So that's looking good. In the oxidation reaction, iodine is our element that isn't oxygen or hydrogen. We've got two on the left and one on the right. So we're going to need to add a coefficient here, a 2, so that we've got two lots of the IO3 minus ion. Now we've got two I's on the left and two I's on the right. So now we've got that first thing balanced, which is the non-oxygen, non-hydrogen atoms, making sure we've got the right number on each side. Our next step is to balance the oxygens by adding H2O. So in our first equation for reduction, we have 3 oxygens on the left and 2 on the right. So we need some more oxygens on the right. So I'm going to add H2O on the right-hand side of my equation there. Now I've got 3 oxygens on the left and 1, 2, 3 on the right. In the oxidation reaction, I have 0 oxygens on the left and I've got 3 times 2, 6 on the right. So I'm going to need to add 6 H2O on the left. So now I've got 6 oxygens on the left and 6 on the right. Okay, great. So now we've balanced our oxygens by adding H2O. Now, since we added oxygens in the form of H2O, we've also added hydrogens. So we're going to balance out the hydrogens by adding H plus ions. So in the reduction reaction, we have 2 hydrogens on the right. That means we need to add 2 on the left. So we're going to add 2 H plus ions on the left of our reduction equation. For the oxidation equation, we have 6 times 2 hydrogens on the left, 12 hydrogens on the left. So we're going to add 12 H plus ions on the right. Okay, so we've balanced out our hydrogens by adding H plus. Our next step is to balance the charges by adding electrons. So looking at our reduction equation, we have 2 H plus ions, so that's 2 positive here. Then we have 1 NO3 minus ion, so that's a negative 1 there. So we've got plus 2, negative 1. On the right-hand side, we've got NO2, which is neutral, 0, and H2O, which is neutral, 0. So on the right-hand side, the net charge is 0. On the left, the net charge is currently positive 1. So we're going to add an electron to the left-hand side. So this gives us a charge of negative 1 here. So we've got 2 plus, minus 1, which overall gives us 0 on the left. And on the right, we've got 0 and 0, which gives us 0 on the right. So we're now balanced for our charge. Let's do the same for our oxidation reaction. So on the left, we have H2O, which has a charge of 0. I2, which has a charge of 0. So overall, we have 0 on the left. On the right, we have 2 sets of IO3 minus. So that's 2 minus there. And we have 12 H plus. So that's positive 12 there. So on the right, we have positive 12 and negative 2. On the left, overall, it's 0. So I'm going to add some more electrons to my right-hand side. I'm going to add 10 electrons. So 10 E minus. That gives me negative 10. So now I've got negative 10, negative 2. That's negative 12 overall. Positive 12 from our H pluses. So that gives us 0 overall on the right. And we have 0 overall on the left. So now that's balanced for charge. Now our next step is going to be to combine these equations together into one big equation. But before we do that, we need to make sure the electrons are going to be balanced. So right now, in our top equation, we have 1 electron on the left-hand side. In the bottom equation, the oxidation equation, we have 10 electrons on the right-hand side. So in order to be able to combine these equations, we need the number of electrons to be the same. So I'm going to multiply my entire reduction equation by 10, so that I have 10 electrons on the left-hand side there. So 10 times 2H plus, that gives me 20H plus. Then I've got 10 NO3 minus and 10 E minus. And on the right, I've got 10 NO2 and 10 H2O. Now I've got 10 E minus on the left on my reduction equation and 10 E minus on the right on my oxidation equation. So that shows that our electrons are going to be balanced when we now add these equations together. I'm going to write this down at the bottom where I've got a bit more room. So on the left-hand side for our reduction equation, we have 20H plus and we have 10 NO3 minus and we have 10 E minus. On the left-hand side of the oxidation equation, we have 6H2O and an I2. Then on the right-hand side, for the reduction, we have 10 NO2 plus 10 H2O. And on the right-hand side for the oxidation, we have 10 E minus plus 2 IO3 minus plus 12 H plus. Okay, so we're ready to now start cancelling some things out. So anything we've got on the left and the right can cancel. So for a start, we've got 10 electrons on the left and 10 electrons on the right. So I'm going to cancel those out. Next, let's look at our H pluses. On the left, we have 20 H plus. On the right, we have 12 H plus. So those can cancel out a bit. So if we subtract 12 H plus on both sides, on the right, that's just going to cancel out our H plus. On the left, we've got 20 minus 12. That's going to leave us with 8 H plus on the left. Okay, our NO3 minus only appears on the left of our equation, so there's nothing to cancel there. For H2O, we've got 6 H2O on the left and 10 H2O on the right. So we can subtract 6 H2O from both sides of our equation. On the left, those are going to cancel out. On the right, we've got 10 minus 6, which is going to give us 4 H2O overall. Our I2 only appears on the left, so there's nothing to cancel there. Our NO2 only appears on the right, so there's nothing to cancel there. And our IO3 minus only appears on the right, so there's nothing to cancel there. Okay, so we've cancelled things out. Let's clean up this equation a bit. So we've now balanced our equation. However, we did this by adding H plus ions. And H plus ions are what we have in an acidic medium. But in the question, it tells us we need to balance it in a basic medium. Basic means we have OH minus ions. So if our question asked us to balance this in an acidic solution, we would be finished. But since it asked about a basic solution, we now have to use OH minus to balance out our H pluses to get rid of those. So right now we have 8H plus on the left. If I add an H plus and an OH minus together, that gives me H2O. So to get rid of my H pluses on the left, I'm going to add 8OH minus. I'm going to add that on the right as well to make sure we're remaining balanced. And on the left, that 8OH minus and 8H plus combine to form 8H2O. So now you can see we've got 8H2O on the left, 4H2O on the right, plus we have 8OH minus on the right. Our final step now is to make sure our H2Os are cancelled out where necessary. Since we have 8 on the left and 4 on the right, we can subtract 4H2O from both sides. So on the right-hand side, those H2Os will just cancel out. On the left, we've got 8 minus 4, which gets us 4H2O. So again, let's clean up this equation by getting rid of the things we've cancelled out. Okay, so let's enter our answers to see if we were correct. So we had 10 NO3 minus ions on the left. We have 1 I2 on the left. And we had 4 H2O on the left. So we've got H2O and we had 4 of them. On the right, we have IO3 minus. We've got 2 of those. For NO2, we've got 10 of those. And finally, we have 8 OH minus. Excellent. So we've gotten that right. The final question asks, how many electrons are transferred in this reaction? So that's asking us to look back to our two half equations that we wrote for reduction and oxidation. Just before we combine those together to form our overall reaction, we balance them to get 10 electrons on the left in the reduction reaction and 10 electrons on the right in our oxidation reaction. So we know that 10 electrons were transferred in this reaction in 1 mole of that equation. So we had 10 electrons transferred. So this was a long process for doing these redox reactions. So just to remind you of the steps, step 1 was going through and figuring out the initial and final oxidation numbers of each element so we could figure out what was oxidized and what was reduced. Next, we split up our equation into 2 parts. One was for the reduction, one was for the oxidation. So anything that was reduced, here it was nitrogen, went in one part of the equation, and anything that was oxidized, here that was iodine, went in the other part of the equation. Then we balanced that. First, we balanced it for the number of atoms of the elements that were not oxygen or hydrogen. So that was nitrogen for our reduction equation and iodine for our oxidation equation. Then we added H2O to balance out any oxygens or hydrogens that we had in our equation. Next, we added H plus ions to balance out any hydrogens that we had. And finally there, we added electrons to balance out our charges. Then we had our 2 half equations done, but before we combined them together, we had to make sure we had the same number of electrons in both. So we ended up having to multiply our reduction equation by 10 in order to have the same number of electrons in both the reduction and oxidation reactions. Our next step was to combine them together. So we wrote out the left-hand side of the reduction plus the left-hand side of the oxidation goes to the right-hand side of the reduction plus the right-hand side of the oxidation. Then we have our complete equation, and all we need to do is cancel out anything that appears on both the left and the right, which means we cancel out our electrons, and we probably cancel out some H2Os or maybe some H pluses as well. If we were doing acidic solution, we would be done at that point, but since we were doing basic solution, we had to add some OH minuses in order to cancel out the H pluses by combining into water. And finally, cancel out any remaining items that were on both the left and right of our equation. So it's a long process, but if you follow those steps, it should work every time for these problems.